Palm trees once grew where only ice exists today. Our planet has experienced dramatic climate reversals, periods when the poles were tropics and crocodiles swam in Antarctic rivers. This is the story of hothouse Earth, a world almost unrecognizable from our own. By the end of this journey, you will understand the powerful forces that can flip our planet's climate and what that means for our future today. How did scientists discover forests at the North Pole, and what triggered these global transformations? The answers lie buried in deep time, challenging everything we assume about a stable world. What does a planet without ice caps truly look like? Earth's history is a book with most of its chapters already written. To read this ancient story, we must first grasp the concept of deep time, a span so vast it challenges our very perception of reality. It is the immense canvas upon which our planet's entire climate saga is painted. Geologists have organized this 4.6 billion-year history into a detailed timeline called the geologic time scale. This is not just a list of dates, it is a narrative structure dividing the planet's life into eons, then eras, and finally into more familiar periods like the Jurassic or the Cretaceous. This framework is our essential map. Without it, we would be lost in the wilderness of billions of years, unable to pinpoint the specific, extraordinary moments when the world flipped. Understanding this grand timeline is the first step to appreciating the true scale of the change, allowing us to travel to those precise intervals when polar ice vanished and lush, warm forests took its place. That fossilized palm frond, chiseled from the Arctic permafrost, is a paradox made of stone. It is a direct message from a world turned upside down, a single piece of a much larger puzzle. These discoveries are not isolated. Across the northern reaches of Canada, scientists have unearthed the stony remains of cypress trees and broadleaf forests, species that today thrive in subtropical climates. Further west in Alaska, the bones of dinosaurs have been found at latitudes that would have plunged them into months of winter darkness. This presented a profound mystery. How could such creatures, many of which were cold-blooded, survive in a land of ice and night? The answer is that the land was not icy at all. The night was warm. This is where a fundamental guiding principle of geology comes into play, a concept called uniformitarianism. It is the simple but powerful idea that the processes we see shaping our world today, like rivers carving canyons or plants leaving imprints in mud, are the same forces that have operated throughout Earth's deep history. We can use the present as a key to unlock the past. So when we find the fossils of alligators and sprawling mangrove roots on an island deep inside the Arctic Circle, we are not just looking at curious rocks. We are reading a climate report. These organisms are biological time capsules. They have specific, non-negotiable requirements for survival. A cold-blooded crocodile cannot generate its own body heat. It would perish in a freezing winter. A palm tree cannot survive a hard frost. Their very presence at the poles is direct, undeniable proof that the entire planet was once enveloped in a profound and pervasive warmth. They are our most reliable witnesses to these ancient greenhouse worlds, offering silent but irrefutable testimony of a time when the planet's thermostat was cranked to its maximum. But fossils are only the first chapter of this story. The true temperature of the ancient world is locked within the rocks and sediments themselves. These geological archives hold chemical secrets, a hidden language we have learned to decode. This field of study relies on what scientists call geochemical proxies. A proxy is a stand-in, a measurable substance that acts as a direct substitute for something we cannot observe, like ancient temperature. The most famous of these is the paleothermometer, a method that reads the climate of the past using the very atoms found in ancient sea creatures. Tiny, single-celled organisms called foraminifera or forams build their delicate shells from minerals in the ocean water. When they die, these shells rain down to the seafloor, accumulating in layers over millions of years. Scientists extract long cores of this sediment, pulling up a continuous timeline of climate history. The key lies in the oxygen atoms within those fossil shells. Not all oxygen atoms are identical. Some are slightly heavier. The ratio of heavy to light oxygen atoms that gets locked into the shell depends almost entirely on the temperature of the water when the organism was alive. By meticulously measuring this ratio in foraminifera shells from different depths in a core sample, researchers can reconstruct the ocean's temperature at that precise moment in deep time, with a precision that can pinpoint differences of just a few degrees. This is not the only chemical detective tool. On land, the waxy coating on ancient leaves preserved in rocks as biomarkers reveals details about rainfall and humidity. The types of clay minerals that form in soils are also controlled by climate, creating a mineralogical fingerprint of warmth and moisture. When the evidence from these different proxies, from the deep sea and the continents, all points in the same direction, the picture becomes undeniable. They collectively tell us that during these hothouse periods, the polar oceans were as warm as a modern tropical lagoon, and the Arctic landmasses experienced average annual temperatures similar to Florida today. This is how we move from knowing it was warm to knowing exactly how warm it was, quantifying a tropical planet with data written in stone and sea. The temperature data locked in those ancient shells and leaves points to a single, inescapable conclusion. Our planet's climate has a master control, a global thermostat governed by the very air itself. Think of Earth's atmosphere as a blanket. A thin layer of certain gases allows sunlight to pass through and warm the surface, but it traps some of the heat that tries to escape back into space. This is the natural greenhouse effect, and it is the reason our world is habitable. Without it, Earth would be a frozen ball of ice. The problem, as the deep time record shows us, is what happens when that blanket becomes too thick. During the ancient hothouse periods, the primary gases thickening that blanket were carbon dioxide and methane. These are the powerful greenhouse engines that can send global temperatures soaring. Where did such immense quantities of these gases come from? The answer lies in some of the most violent and transformative events in our planet's history. The most significant driver was often catastrophic volcanic activity on a scale we can barely comprehend. These were not single mountains erupting, but entire regions, known as large igneous provinces, cracking open and flooding the landscape with lava for hundreds of thousands, even millions of years. This was geology on overdrive, pumping staggering amounts of carbon dioxide directly into the atmosphere in a relentless, planet-altering pulse. But the warming did not stop with the volcanoes. As the oceans heated up, they triggered a second, even more potent feedback. Vast reservoirs of frozen methane, stored in icy cages on the seafloor called methane hydrates, began to destabilize and melt. Methane is a far more powerful, though shorter-lived, greenhouse gas than carbon dioxide. Its release into the atmosphere would have supercharged the warming, creating a runaway greenhouse effect. This process reveals the delicate balance of the planetary carbon cycle. Carbon is constantly moving between the air, the ocean, life, and rocks. Volcanoes and methane seeps are sources, adding carbon to the atmosphere. Meanwhile, processes like the weathering of rocks and the burial of dead organisms act as sinks, slowly pulling carbon back down. For millions of years at a time, these hothouse periods represent a dramatic tipping of the scales. The sources of carbon wildly overwhelmed the planet's ability to remove it. the atmosphere's composition shifted, the blanket grew heavy, and the planet's thermostat was cranked to its maximum setting, transforming the entire world into a place where forests could conquer the poles. The reign of the dinosaurs coincided with one of the most profound and long-lasting greenhouses in Earth's history. For nearly 200 million years, the planet was a world of intense heat, a place where the very geography of life was shaped by warmth. This was the Mesozoic era, a time when the poles were not just ice-free but were verdant, living landscapes. At the top of the world, in what is now northern Alaska, herds of duck-billed dinosaurs like Edmontosaurus trudged through lush coastal wetlands. They were not migrating to escape a brutal winter. They were permanent residents of a land that knew no frost. These were the polar dinosaurs, creatures that adapted to a unique environment of perpetual summer light and long, dark winters, yet never saw a snowflake. The proof is not just in their bones, but in the very ground they walked on. Deep in the Antarctic mountains, geologists have uncovered thick, black seams of coal, the compressed remains of ancient swamp forests that once thrived just a few hundred miles from the South Pole. These are the fossilized energy of a warm climate, a direct contradiction to the frozen desert that exists there today. This global sauna was fueled by a perfect storm of geological events. The ancient supercontinent of Pangaea, which had once gathered all the world's landmasses into one giant entity, was slowly, inexorably tearing itself apart. As the continents fractured and drifted, new ocean basins were born. This reshaping of the world's plumbing had a dramatic effect on global climate. Vast, unobstructed ocean currents began to circulate, acting like a planetary heating system. These powerful currents, like a massive conveyor belt, transported immense amounts of heat from the steamy tropics all the way to the high latitudes. Warm water bathed the polar coastlines, moderating temperatures and preventing the formation of ice, even during the months of total winter darkness. The planet became a more efficient, more evenly heated place. The breakup of Pangaea also triggered a massive increase in volcanic activity along the newly forming mid-ocean ridges. These underwater mountain chains spewed colossal amounts of carbon dioxide into the atmosphere for millions of years, thickening the planetary blanket to an extreme degree. The Cretaceous period represents a stunningly different mode for our planet's climate system, a sustained experiment in what happens when the global thermostat is broken, stuck permanently on high. How did life not just survive but thrive in this world of endless summer? That long, stable greenhouse of the dinosaurs eventually gave way, but the planet's capacity for extreme warming was far from exhausted. A new chapter of climate chaos was about to be written, one that unfolded not over millions of years, but in a terrifyingly brief geological instant. 56 million years ago, at the dawn of the age of mammals, Earth experienced a planetary fever spike known as the Paleocene-Eocene thermal maximum. This was not a gradual warming, it was a sudden, violent lurch in the global climate system. In the span of just a few thousand years, a geological blink of an eye, average global temperatures skyrocketed by 5 to 8 degrees Celsius. The deep sea, typically a stable, cold environment, became a warm bath, with bottom waters reaching well over 20 degrees. To understand the sheer speed of this event, picture the climate change we are witnessing today, but compressed into a time frame shorter than the entire history of human civilization. The evidence for this catastrophe is etched into the chemistry of the ocean floor. Scientists drilling into deep-sea sediments find a distinct dark layer from this time. Within that layer, the fossil shells of tiny foraminifera tell a shocking story. They reveal what is called a massive negative carbon isotope excursion. In simple terms, this means that a huge amount of very specific type of carbon, the kind that comes from living things or from deep within the Earth, was suddenly dumped into the atmosphere and ocean. It is a chemical signature of a planet-scale carbon overdose. What could possibly release so much carbon so quickly? The leading suspect is a powerful 1-2 punch. Intense volcanic activity began to warm the planet, likely from a large igneous province erupting in the North Atlantic. This initial pulse of heat was enough to destabilize the planet's most sensitive carbon reserves. Vast deposits of frozen methane, locked in icy cages called clathrates on the continental shelves, suddenly thawed. Billions of tons of this potent greenhouse gas bubbled up from the seafloor and into the atmosphere, igniting a runaway greenhouse effect. The planet was essentially poisoning itself with its own stored carbon. The Paleocene-Eocene thermal maximum stands as a stark warning from deep time. It proves that our climate system has triggers that can cause it to tip rapidly into a new, hotter state, with changes that are both dramatic and, from a human perspective, permanent. That sudden fever spike of the Paleocene-Eocene thermal maximum eventually subsided, but the planet was already on a slow, inexorable path toward a cooler future. This long-term shift was not driven by volcanoes or methane, but by a far more powerful and gradual force. The very ground beneath our feet is in constant, slow motion. This is the grand unifying theory of geology, plate tectonics. The continents are not fixed, they are massive rafts of granite, adrift on a sea of molten rock. Over millions of years, their slow dance across the globe has repeatedly rewritten the entire planetary climate system, opening and closing oceanic gateways that rerouted the great currents of the sea. The formation of the Antarctic ice sheet, the very symbol of a frozen pole, was a direct result of this continental choreography. For most of Earth's history, Antarctica was not a solitary continent. It was connected to South America and Australia, part of a larger landmass that blocked the free flow of water around the southern pole. Then, around 30 million years ago, a critical gateway began to open. The Drake Passage, the treacherous body of water between the tip of South America and the Antarctic Peninsula, was born. This seemingly small geological event had a monumental consequence. With no land in the way, a powerful new current could form, the Antarctic Circumpolar Current. It became an unimpeded river of seawater, flowing endlessly around Antarctica. This current acted as a massive barrier, a moat of cold water that effectively isolated the southern continent from the warm tropical currents that had once kept it mild. Antarctica was now trapped in its own frigid prison, cut off from the planet's central heating system. The result was a slow, relentless cooling that allowed snow to accumulate, season after season, millennium after millennium, until it compacted into the vast ice sheets we know today. The world had one frozen pole, but this tectonic story has a flip side, a mechanism for creating global warmth. Before the age of the dinosaurs, a vast, shallow ocean known as the Tethys Sea stretched across the tropics, separating the ancient northern and southern supercontinents. This warm body of water was a colossal engine for distributing heat and moisture across the planet. Over time, as Africa and India drifted northward, they collided with Eurasia, slowly squeezing the Tethys Sea out of existence. This closure, which created mountain ranges like the Alps and the Himalayas, dramatically altered the world's weather patterns. The great equatorial heat reservoir was gone. The new mountains disrupted airflow, intensifying seasonal monsoons in some regions and creating vast, arid deserts in others. Crucially, the destruction of the Tethys altered ocean circulation, preventing the efficient transfer of tropical warmth to the higher latitudes. The arrangement of continents and oceans is the ultimate architect of our climate. building and dismantling ice ages and hothouses over millions of years. This raises a profound question about our own time. What happens when a force as powerful as plate tectonics, but operating at a blindingly faster speed, enters the picture? While the slow dance of continents sets the stage for climate over millions of years, a far more delicate rhythm dictates the tempo of ice ages. This rhythm is conducted not from within the Earth, but from the heavens by the subtle gravitational pull of the Sun, Moon, and planets. These are the Milankovitch cycles, the predictable, repeating variations in Earth's orbit and tilt that act as a master metronome for our planet's climate. They are the gentle pulse behind the great freezing and thawing of the ice ages. The first of these three rhythms is eccentricity, which describes the shape of Earth's path around the Sun. Our orbit is not a perfect circle, but a slight oval that becomes more or less stretched over a cycle of about 100,000 years. When the orbit is more elliptical, the Earth receives significantly more solar energy when it is closest to the Sun, and less when it is farthest away, creating more extreme seasonal contrast. The second cycle is axial tilt. Our planet leans on its side, and this tilt, which gives us our seasons, is not constant. It wobbles between about 22 and 24.5 degrees over a 41,000-year cycle. A greater tilt means more dramatic seasons with hotter summers and colder winters, especially in the high latitudes. The third rhythm is precession, a slow wobble in Earth's rotational axis, much like the wobble of a spinning top. This cycle, which takes about 26,000 years, changes which hemisphere is pointed toward the Sun during its closest approach, determining whether a given hemisphere will have more intense summers or milder ones. Alone, each of these cycles causes only a tiny variation in the amount of sunlight reaching different parts of the Earth, but when they align in just the right way, they can tip the balance. A combination of low eccentricity, less tilt, and the wrong phase of precession can lead to cool summers in the northern hemisphere, summers so mild that they fail to melt all of the previous winter's snow. This is the trigger for an ice age. A small amount of snow persists, reflects more sunlight, cools the area further, and over thousands of years, a feedback loop builds an ice sheet. Yet these orbital cycles do not act alone. Their power is entirely dependent on the atmospheric background. Think of Earth's climate as a piano. The Milankovitch cycles are the fingers playing the keys, producing the melody of ice ages and interglacials. But the volume of that music is controlled by the level of greenhouse gases in the atmosphere. During a cold, low carbon dioxide period, like the ice ages of the last few million years, the orbital rhythm produces a loud, clear signal, advancing and retreating glaciers in time with the celestial beat. But even during the deep hothouses, when carbon dioxide levels were sky-high and the poles were warm, this metronome was still ticking. The music was just much softer. The orbital cycles still caused significant climate variability, shifting rainfall patterns and altering temperatures enough to leave a distinct signature in the rock record. These subtle, repeating bands in sedimentary layers are the fossilized heartbeat of our planet, a rhythm written in stone, proving that even in a world of tropical poles, the gentle sway of our planet in space still called the tune. That celestial metronome, the steady rhythm of our orbit, relies on a sun whose power we take for granted. Yet the sun itself has a history, and its past reveals one of the most profound mysteries in our planet's story. Billions of years ago, when life was first emerging, our sun was a different star. Nuclear fusion in its core was less efficient, making it significantly dimmer. By all rights, a younger, fainter sun should have meant a frozen, lifeless Earth for its first 2 billion years. The entire planet should have been a ball of ice. But the geological record tells a completely different story. We find evidence of liquid water, of rivers carving valleys, and even of warm intervals, all during this time of weak sunlight. This is the faint young sun paradox, a contradiction between astrophysics and geology that challenges our understanding of planetary survival. How did Earth avoid becoming a permanent snowball? The answer lies not in the heavens but in the ancient air itself. Our planet's early atmosphere was a vastly different blanket, one woven from much more potent greenhouse gases. Scientists believe it was likely far thicker with carbon dioxide and, crucially, methane. Methane is an incredibly powerful greenhouse gas, and in an oxygen-free world, it could build up to high concentrations, creating a supercharged insulating layer. This dense atmospheric cloak trapped every bit of heat the faint sun could provide, effectively compensating for the stellar weakness and keeping the planet warm enough for water to flow and for life to begin. But this delicate balance was destined to be broken by life itself. The rise of photosynthetic cyanobacteria, tiny organisms that began harnessing sunlight to produce energy, marked a turning point. Their waste product was oxygen, a gas that was poisonous to most early life and one that reacts chemically with methane, breaking it down. The Great Oxidation Event, around 2.5 billion years ago, was a planetary catastrophe for the methane greenhouse. As oxygen levels rose, the methane blanket was torn away. The planet plunged into its first, and possibly most severe, ice age, a global winter that may have frozen the oceans from pole to pole. This paradox reveals a stunning truth. Earth's climate has never been a simple result of solar output. It is a complex dance between the light from our star and the ever-changing chemistry of our air, a partnership where life itself can become a powerful geological force, capable of both maintaining a habitable world and nearly destroying it. This ancient dance between the faint sun and a thick atmosphere reveals a planet whose climate is governed by a deep, rhythmic cycle. The very carbon that threatens to overheat our world today is the same element that has always been on the move, flowing between the air, the sea, the rocks, and life itself. This is the geological carbon cycle, the planet's long-term breathing mechanism. For most of Earth's history, this cycle has maintained a remarkable balance, thanks to a slow but powerful natural thermostat. Primary cooling agent is something you walk on every day, ordinary rock. In a process called silicate weathering, rainfall, which is naturally slightly acidic, reacts with rocks like granite and basalt. This chemical reaction slowly pulls carbon dioxide out of the atmosphere, dissolving it and washing it down rivers into the oceans. It is a gradual, relentless cleansing of the air, a process that operates over hundreds of thousands of years. This is the planet's primary brake on runaway warming, a slow and steady force that can, given enough time, counteract even the most intense volcanic eruptions. But what happens when the eruptions do not stop? The history of our planet is punctuated by events where the brakes failed and the carbon cycle slammed into overdrive. The most dramatic examples are the flood basalt events, like the formation of the Siberian traps 250 million years ago. This was not a single volcano. It was a continental wound, a region in modern-day Russia that cracked open and spewed lava over an area larger than Europe. For nearly 1 million years, it vented colossal quantities of carbon dioxide and sulfur dioxide directly into the atmosphere. This was a carbon release event so rapid and so massive that it completely overwhelmed the slow, weathering thermostat. The planet's natural ability to remove carbon was utterly dwarfed by the rate at which it was being injected. The atmosphere's composition shifted violently. The greenhouse blanket smothered the planet, and global temperatures soared, leading to the greatest mass extinction in Earth's history. While volcanoes pump carbon into the air, the oceans and life work tirelessly to pull it back out. In the sunlit surface waters, microscopic plankton absorb dissolved carbon dioxide to build their shells. When they die, these tiny shells, along with other organic debris, sink like a constant marine snowstorm into the dark, deep ocean. This is the biological pump, a vital process that effectively transfers massive amounts of carbon from the atmosphere to the deep sea, isolating it from the climate system for centuries. But the most permanent form of carbon sequestration happens when this process is written in stone. Those tiny sinking shells are made of calcium carbonate. On the seafloor, over millions of years, they accumulate into thick layers of ooze that, under pressure, are transformed into limestone. This is the ultimate destiny for a vast amount of atmospheric carbon, locked away in the white cliffs of Dover and in limestone formations across the globe. It is Earth's long-term carbon storage vault. The story of our climate is a story of competing rates, a battle between the slow, patient removal of carbon by rock weathering and marine life, and the sudden, catastrophic release from geological events. The planet always recovers its balance, but the geological record shows us that the recovery time is written in millions of years, a timescale that redefines the word permanent. The geological carbon cycle can be pushed to a breaking point, and the most terrifying proof lies 250 million years in the past. At the close of the Permian period, the planet experienced a cataclysm so severe it nearly ended life itself. This was the end Permian extinction, an event so devastating it is known simply as the Great Dying. In the span of perhaps just 60,000 years, a geological heartbeat, 96% of all marine species and 70% of terrestrial vertebrate species vanished forever. The trigger was not an asteroid, but the Earth itself turning against its inhabitants. In what is now Siberia, the crust fractured on a continental scale. This was the birth of the Siberian Traps, a volcanic event of almost unimaginable violence. For hundreds of thousands of years, lava flooded from fissures not for days or weeks, but for millennia, covering millions of square miles in basalt. The lava flows were only part of the catastrophe. The real killer was the gas. The volcanoes pumped staggering quantities of carbon dioxide directly into the atmosphere, an amount that may have dwarfed all of humanity's fossil fuel emissions. This initial pulse of carbon dioxide began to thicken the planetary blanket, triggering a global fever, but the warming likely unlocked a second, even deadlier reservoir. Vast stores of methane frozen in seafloor sediments may have destabilized and burst into the atmosphere, supercharging the greenhouse effect and sending global temperatures soaring by perhaps 10 degrees Celsius. The world became an oven. On land, the interior of the supercontinent Pangaea transformed into a scorching desert, where only the hardiest life could cling on. But the true horror unfolded in the oceans. The excess carbon dioxide did not just stay in the air. It dissolved into the seawater, forming carbonic acid in a process we now call ocean acidification. The seas, the cradle of life, became corrosive. For any creature that built a shell or skeleton from calcium carbonate, the water itself became a poison. The chemical change was so rapid that their shells literally dissolved, or they could not form them at all. This acidic, warming water also lost its oxygen. The oceans became stratified, with warm, stagnant layers on top preventing oxygen from mixing into the depths. Vast stretches of the global ocean turned into dead zones where only bacteria that thrived in poison could survive. We see the evidence of this in the rocks from that time, a layer where diverse fossil communities abruptly vanish, replaced by a thin, grim band populated only by the few species that could endure this hellish world. The Great Dying stands as the ultimate cautionary tale from deep time. It demonstrates that when the planet's carbon cycle is violently disrupted, the consequences are not merely a shift in temperature, but a cascading collapse of the very systems that support life. It is a stark reminder of the fragility of our global ecosystem when pushed beyond its limits. Our familiar world of ice and snow is a geological novelty. For the vast majority of its 4.6 billion-year history, Earth has been a planet without permanent polar ice caps. The global freezer we live in today is a recent development, a brief and unusual chapter in an otherwise warm story. The descent into this icehouse world began in earnest around 34 million years ago. Antarctica, now fully isolated by the frigid moat of the circumpolar current, saw its lush forests wither and die. Snow that once melted in the summer began to persist year after year, century after century, slowly compacting under its own weight into a crushing sheet of ice. This was not a sudden event, but a slow, relentless transformation, turning a green continent into a white desert. But the planet was not finished cooling. For millions of years, the northern hemisphere remained largely ice-free. Then, a second tipping point was crossed just 2.7 million years ago. The great ice sheets of the northern hemisphere began to grow, blanketing North America and Eurasia in glaciers miles thick. What made this dual freezing possible? It was a perfect and rare confluence of conditions. The continents were in the right positions, with land masses sitting over both poles, allowing snow to accumulate on solid ground. Atmospheric carbon dioxide had dropped to a low level, too thin a blanket to hold onto the sun's heat. And into this cool, predisposed world, the steady rhythm of the Milankovitch cycles began to play its melody. The gentle wobbles in Earth's orbit provided the precise timing for the ice to advance and retreat in a rhythmic dance of glaciation. We think of our world as the default setting, but from the perspective of deep time, we are living in an anomaly, a brief icy interlude between much longer ages of global warmth. These geological clues provide a static picture, a collection of frozen moments, but how do we animate these fragments into a living, breathing world? The answer lies in one of the most powerful tools of modern science, paleoclimate modeling. Scientists use supercomputers to run incredibly complex programs called general circulation models. Think of these as digital time machines. Researchers feed them all the available data, the reconstructed maps of ancient continents, the estimated levels of carbon dioxide from rock chemistry, and even the slightly dimmer output of the young sun. The model then calculates the physics, simulating the flow of the atmosphere and the oceans to recreate a dynamic, three-dimensional vision of a vanished Earth. It is a virtual planet built from code and data where we can watch the weather patterns of the Cretaceous unfold before our eyes. How do we know if these simulations are accurate? This is where the geological evidence becomes the ultimate test. Scientists compare the model's predictions, its output for temperature or rainfall, with the real-world data from the proxy records. Do the model's polar temperatures match what the fossilized palm fronds and oxygen isotopes tell us? If a simulation of the Eocene greenhouse predicts a swampy, warm coast in the Arctic, and we then find the coal seams and alligator fossils to prove it, we know the model is on the right track. This process of validation turns a theoretical exercise into a reliable window into the past. These digital worlds allow us to run experiments that are impossible in reality. We can ask what would happen if we removed a key oceanic gateway or doubled the carbon dioxide levels in a Triassic world. The models show us how heat was transported by ancient currents to keep the poles warm, and they can reveal the patterns of intense monsoons that would have drenched the interior of Pangaea. They transform a collection of clues into a coherent story, giving us a dynamic view of our planet's most extreme and alien chapters. A world of endless summer demanded a new kind of life. For millions of years, the hothouse Earth was not a barren wasteland but a cradle of evolutionary innovation, where species were forged in the crucible of extreme warmth. The fossil record reveals a planet teeming with biological creativity, as plants and animals developed remarkable strategies to thrive in this global greenhouse. Consider the polar dinosaurs of Alaska. Living at latitudes that experienced months of winter darkness, these creatures could not simply migrate south. They were permanent residents of a warm yet seasonally dark world. How did they survive? Evidence suggests they possessed extraordinary adaptations. Some, like the small, feathered theropods, may have had insulating coats to retain body heat during the cool polar nights. Larger herbivores, like the duck-billed Edmontosaurus, likely lived in herds and browsed on the lush, resilient vegetation that grew around the clock during the summer months. Their large body size, a common trait in colder regions even today, would have helped them conserve heat more efficiently. This was not a desperate struggle for survival, but a testament to life's ability to carve out a niche in even the most challenging corners of a warm planet. The forests themselves were a key part of this story. With carbon dioxide levels several times higher than today, the ancient atmosphere acted as a supercharged fertilizer. Plants grew with explosive vigor, leading to the spread of dense tropical forests that reached the very poles. The ancestors of today's magnolias, sycamores, and cycads formed vast woodlands where now there is only tundra and ice. This botanical boom created a feedback loop, as the proliferation of plant life accelerated the weathering of rocks, a slow but vital process that helped regulate the planet's carbon cycle over millions of years. Life was not just responding to the climate, it was actively participating in it. The great migrations of entire ecosystems were another dramatic response. As the planet warmed, climate zones shifted poleward. Creatures and plants adapted to warm, wet conditions found new habitats opening up for them in higher latitudes. We can trace the movement of mammals across northern continents during the intense heat of the Paleocene-Eocene thermal maximum. Smaller, early mammals with generalized diets suddenly found themselves in a world of abundant subtropical forests. This rapid environmental change acted as an evolutionary pressure cooker. In the ecological vacuum left by the extinction of the dinosaurs and spurred on by the heat, mammals underwent an explosive diversification. New forms emerged, from the earliest ancestors of horses and primates to specialized predators, all within a geological instant. This period of extreme stress became a catalyst for one of the most important radiations in the history of life. The dance between climate and evolution is a constant throughout deep time. A shift in the world's temperature is not merely a change in the weather, it is a rewrite of the rules of existence. It favors the generalist over the specialist, the adaptable over the rigid. It opens new highways for migration while closing others, and in doing so, it forces life to innovate, to experiment, and to evolve. The lush, alien world of the hothouse Earth was not a static paradise, but a dynamic and ever-changing stage for this grand biological drama. The geological clock is now ticking at a human pace. Our industrial civilization has become a geological force, releasing carbon dioxide into the atmosphere at a rate that challenges even the most violent episodes in Earth's deep history. The parallels are both striking and sobering. The immense volcanic pulses of the past and the sudden methane burps of the Paleocene-Eocene thermal maximum were planetary-scale carbon release events. Today, humanity is conducting a similar, uncontrolled experiment, but with one critical difference: speed. During the Paleocene-Eocene thermal maximum, the natural world injected roughly 4.5 billion tons of carbon into the atmosphere over a few thousand years. Humanity now matches that entire release in a single decade. We are replicating one of the planet's most extreme climate events, but compressing its most destructive phase into the span of a single human lifetime. This is not a gradual shift. It is a geologically instantaneous shock to the entire Earth system. What does the deep time record suggest will happen next? The past does not offer a perfect one-to-one map of our future, but it provides a vital playbook of the Earth's likely responses. The most certain and long-lasting consequence is sea level rise. During past warm periods when the poles were tropics, there were no continental ice sheets. The Greenland and Antarctic ice caps contain enough frozen water to raise global sea levels by over 200 feet. The transition from an ice house to a hothouse world is fundamentally a transition from a planet with coastlines to a planet without them. The fossilized shorelines of ancient seas, now stranded high inland, are a permanent record of this reality. The Deep Time Archive also warns of a second, more insidious threat, the acidification of the oceans. We already see the chemical signature of this in the end Permian extinction layer, where the seas became corrosive and stripped of life. The same process is underway today as the ocean absorbs our excess carbon dioxide, threatening the entire marine food web from the tiny shell-building plankton to the great coral reefs. Perhaps the most profound lesson from deep time is the inevitability of ecosystem reorganization. The world will not simply become a warmer version of itself. It will transform into a new state with climate zones, rainfall patterns, and biological communities reshuffling on a global scale. The fossil record shows us that during past warmings, life did not merely adapt in place, it migrated. Entire biomass marched poleward following the warmth. Creatures found themselves in new and unfamiliar alliances, competing for resources in landscapes that were constantly changing. The planet's biodiversity was ultimately reshaped by these events, with some lineages flourishing and others vanishing forever. The Earth system has thresholds, and the evidence written in stone tells us that we are pushing hard against them. The climate of the past reveals the profound sensitivity of our world to major perturbations. It shows us that a relatively small shift in the composition of the air can rewrite the map of the entire planet for millennia to come. The real question is not whether the Earth will change, but what kind of world we choose to create with the powerful geological forces we have now unleashed. These powerful forces from the past reveal a climate system with built-in points of no return. We are now navigating a landscape of climate tipping points, critical thresholds where a small nudge can unleash a cascade of changes, locking the planet into a new and often irreversible state. Think of it not as a gentle slope but as a series of dominoes. Once the first one is pushed past its balance point, the fall of the others becomes automatic, driven by their own momentum. The geological record is filled with evidence of these domino effects in action. One of the most potent and visible examples is the ice albedo feedback. Albedo is simply a measure of how much sunlight a surface reflects. Fresh snow and ice are brilliant white, reflecting up to 90% of solar energy back into space. But when warming temperatures cause this ice to melt, it reveals the much darker land or ocean underneath. These dark surfaces are greedy, absorbing up to 90% of the sun's heat instead of reflecting it. This local warming causes more ice to melt, which exposes more dark surface, which absorbs more heat in a self-reinforcing loop. This is not a future prediction. We see this domino beginning to fall today in the Arctic, where the loss of sea ice is accelerating the region's warming at more than twice the global average rate. The past shows us that once this process gains momentum, it can lead to the complete loss of an ice sheet, a change that then defines the planet for millions of years. But the ice albedo effect is just one domino in a long and dangerous chain. Locked within the frozen soils of the far north lies another sleeping giant, permafrost. This ground has been frozen for thousands of years, and it holds a massive stockpile of dead plant matter, a vast store of ancient carbon. As the Arctic warms, this permafrost begins to thaw. The previously frozen organic matter is unlocked, and microbes begin to feast upon it. Their digestion releases either carbon dioxide or, in waterlogged conditions, methane, a greenhouse gas far more potent than carbon dioxide over the short term. This release of gases amplifies the atmospheric warming, which in turn causes more permafrost to thaw, releasing more carbon. It is a vicious, self-fueling cycle that could one day shift the Arctic from being a carbon sink to a major carbon source, pouring fuel on the fire of global warming. These feedbacks are not confined to the polar regions. The great tropical forests, like the Amazon, are also vulnerable to a tipping point. The Amazon generates much of its own rainfall through the constant evaporation and transpiration from its billions of leaves. This creates a dense, moist atmosphere that sustains the forest, but widespread deforestation and rising temperatures can disrupt this delicate hydrological cycle. If too much forest is lost, the system may become too dry to support a rainforest, triggering a dieback where large areas could shift to a savanna-like state. This transformation would not only be a catastrophic loss of biodiversity, it would also release the immense amount of carbon stored in the trees and soils, delivering another powerful blow to the global climate system. The history of our planet is written in these cascading events. The transition from a greenhouse to an icehouse world was not a single event, but a series of tipping points crossed over millions of years, from the isolation of Antarctica to the drawing down of atmospheric carbon. Conversely, the plunge into the hothouse of the Paleocene-Eocene thermal maximum was a cascade of warming and carbon release that unfolded in a geological instant. These past episodes demonstrate the inherent instability of the climate system when pushed too far. They show us that the real danger is not the initial push, but the domino effect that follows, an avalanche of change that can rapidly reshape the world for generations to come. Recognizing these thresholds from deep time is our most urgent task, a vital key to understanding the risks we face today. 3 million years ago, our planet was in a state that holds a startling mirror up to our own time. This was the mid-Pliocene warm period, a chapter in Earth's history when the amount of carbon dioxide in the atmosphere was almost identical to what we have today. Yet the world it created was profoundly different. Global temperatures were 2 to 3 degrees Celsius warmer on average. The northern hemisphere was largely free of ice sheets, and sea levels lapped shores that were over 20 meters or 65 feet higher than our current coastlines. How do we know this? The evidence is written across the globe. In the American West, you can find ancient beach deposits stranded high in the desert, far from any ocean. Fossilized shells of warm water plankton, found in sediments that now lie in the chilly North Atlantic, tell a story of seas that were several degrees warmer. These are not just random clues, they are consistent pieces of a global puzzle, pointing to a planet that was uniformly and significantly hotter than our pre-industrial world, even with the same basic atmospheric ingredient. This presents a central mystery. If the carbon dioxide level was the same then as it is now, why was the Pliocene world so much warmer? The answer lies in the subtle, powerful context of time and Earth's own slow adjustments. The Pliocene warming was not a sudden shock. It was a gradual climb over thousands of years, driven by natural, slow-moving shifts in the Earth's orbit, and the slow leakage of carbon dioxide from the ocean or from occasional volcanic activity. This leisurely pace allowed the planet's entire system to settle into a new equilibrium. The slow warming triggered a cascade of feedbacks that amplified the initial heat. As ice sheets in the northern hemisphere gradually retreated, they exposed darker land and ocean, which absorbed more of the sun's energy, leading to more warming. As the planet heated, the atmosphere could hold more water vapor, which is itself a potent greenhouse gas, thickening the atmospheric blanket even further. The Pliocene world had also not yet settled into the exact continental configuration we know today. The Central American Seaway, a narrow ocean passage between North and South America, was still partially open. This altered global ocean currents, allowing more warm water to circulate between the Atlantic and Pacific, which likely contributed to distributing heat more evenly across the globe and preventing the buildup of polar ice. The mid-Pliocene, therefore, is not a perfect prediction of our future. It is something far more valuable, a completed experiment. It shows us the kind of world that our current level of carbon dioxide can ultimately sustain once the entire climate system, from the ice sheets to the oceans, has fully responded. We have injected the same amount of carbon into the air, but we have done it in a geological instant, not over millennia. Our world is still catching up to the heat that is already guaranteed. The Pliocene gives us a glimpse of the destination we are speeding toward, a world whose map was redrawn by a familiar number in the air. The health of our planet's great heat engine, the ocean, hangs in a delicate balance. For millions of years, a slow and mighty river has flowed within the sea, a global conveyor belt of currents that fundamentally shapes our climate. This immense circulation is driven by differences in water temperature and saltiness. Warm, salty water from the tropics travels northward on the surface, releasing its heat into the atmosphere and warming regions like northern Europe. As this water cools and becomes denser in the high latitudes, it sinks into the abyss, beginning a long, deep journey back toward the equator. This constant churning is a planetary life support system, efficiently distributing the sun's energy and preventing the tropics from boiling over and the poles from freezing solid. During ancient hothouse periods, this system was even more vigorous. With no polar ice to create cold, dense sinking water, the circulation was likely driven more by salt, creating a world where warm currents bathed the coastlines of Antarctica and kept the Arctic lush and green. But this system has a fragile trigger. What happens if this great conveyor belt slows down or, in a worst-case scenario, stops entirely? We are already seeing early warning signs of a slowdown in the Atlantic branch of this circulation, known as the Atlantic Meridional Overturning Circulation. A significant disruption would not simply cool the North Atlantic. It would scramble global weather patterns, shifting rainfall belts that billions depend on for agriculture, and potentially plunging some regions into a deep chill, even as the planet as a whole continues to warm. The ocean's currents are the arteries of our climate, and their stability is not guaranteed. Beyond moving heat, the sea performs another vital function, one that comes at a great cost. The world's oceans have absorbed nearly a third of the carbon dioxide we have released by burning fossil fuels. This has acted as a crucial buffer, slowing the rate of atmospheric warming and buying us precious time. But this service has a severe price, a chemical reaction that is changing the very nature of the seawater. When carbon dioxide dissolves in the ocean, it forms carbonic acid, the same weak acid found in soda. This process, called ocean acidification, lowers the water's pH, making it more corrosive. For any creature that builds a shell or skeleton from calcium carbonate, from microscopic plankton to sprawling coral reefs, this is a direct threat. In more acidic water, it becomes energetically costly and eventually impossible for them to form their protective structures. Their shells simply dissolve. We have seen this movie before. The geological record from the end Permian mass extinction shows a stark layer where diverse fossil communities vanish, replaced by the few species that could tolerate acidic, oxygen-poor seas. The same chemical signature is now appearing in our modern ocean. The plankton that form the base of the marine food web, the oysters and clams that feed coastal communities, the great coral ecosystems that shelter a quarter of all marine life, all are vulnerable. The ocean has been our silent partner, absorbing our excesses and masking the true scale of the problem. But its capacity is finite, and the bill for this service is now coming due, written in the changing chemistry of the sea. But for every force that warms the planet, nature possesses a powerful, if temporary, antidote. High above our heads, suspended in the thin air, float countless microscopic particles known as aerosols. These tiny fragments of dust, ash, and sea salt act as a planetary sunshade, reflecting a portion of the sun's incoming energy back into space and cooling the surface below. This is the other side of the atmospheric coin, a constant tug of war between the warming blanket of greenhouse gases and this reflective veil of particles. The most dramatic demonstrations of this cooling power come from the Earth's own interior. A massive volcanic eruption can blast millions of tons of sulfur dioxide gas high into the stratosphere, where it transforms into tiny sulfate aerosols. This man-made shroud can circle the globe for years, dimming the sun and lowering average temperatures across the entire planet. We have witnessed this in recorded history. The colossal 1815 eruption of Mount Tambora in Indonesia led to the infamous year without a summer in 1816. Frosts blackened crops in New England during June and July, and snow fell in Europe in August, causing widespread famine. This was a sudden, dramatic shock to the global system, a vivid reminder of how sensitive our climate is to these high-flying particles. Yet this volcanic cooling is always fleeting. Within a few years, those sulfate particles drift back down to Earth, and the sun's full strength returns. The relentless, long-term warming from the carbon dioxide released by the same volcano remains, slowly accumulating in the atmosphere for centuries. This highlights the fundamental difference between these two forces. Greenhouse gases are a persistent change to the atmosphere's composition, a long-term investment in heat. Aerosols are a short-term withdrawal of sunlight, a temporary check against warming that is quickly spent. This battle is not confined to volcanoes. A similar, but far more catastrophic, process occurs when an asteroid strikes the Earth. The impact of a massive space rock does not just create a crater. It vaporizes rock and hurls immense quantities of dust and soot high into the atmosphere, blocking out the sun for months or even years. This is an impact winter, a sudden, deep freeze triggered by a celestial collision. Scientists believe it was this very mechanism, following the asteroid impact 66 million years ago, that contributed to the extinction of the dinosaurs. The world did not end with fire alone, but with a long, dark chill that collapsed food webs worldwide. Our climate is perpetually balanced on a knife edge between these competing influences, a system where the slow, patient work of carbon dioxide can be momentarily countered by the violent, brilliant reflection of a speck of dust. Earth's wild climate history is not just a story about our past, it is a guidebook for the search for other living worlds. For decades, the hunt for alien life has centered on a simple, elegant idea: the habitable zone. This is the orbital region around a star where temperatures are just right for liquid water to exist on a planet's surface. It is often called the Goldilocks zone, not too hot and not too cold. But our own planet's journey reveals that this concept is too static. Distance from the Sun is only the starting point. The true controller of a world's climate is its atmosphere. Venus and Mars both lie within the fringes of our Sun's habitable zone, yet one is a scorching, acidic hellscape and the other is a frozen, barren desert. Their fates were sealed not by their location but by the composition of their air. A planet with a thick carbon dioxide blanket, like ancient Earth during its hothouse periods, could remain warm and watery even if it were nudged slightly further from its star. Conversely, a world with a thin atmosphere, or one that has lost its greenhouse gases, could become a global ice ball even if it orbits well within the theoretical habitable zone. We now know that our galaxy is filled with such worlds, exoplanets frozen in climatic extremes. Some are eternal hothouses, perhaps tidally locked to their stars with one side in perpetual, scorching daylight and the other in endless night. Others might be snowball planets, entire globes encased in ice, their oceans sealed away under a frozen crust, much like Earth may have been during its own severe ice ages. The key to whether any of these worlds are truly alive is the same force that has repeatedly rescued Earth from climate catastrophe: geology. A planet's volcanic breath, its tectonic rumblings, and the slow weathering of its rocks create a planetary thermostat. This geological carbon cycle can pull a world back from the brink of a runaway greenhouse or a global freeze, potentially maintaining stable conditions for long enough for life to gain a foothold and evolve. When we look at the fossil evidence of crocodiles swimming in the Arctic or coal seams buried in Antarctica, we are not just studying our own history. We are expanding our definition of a living world. We learn that life is tenacious, capable of adapting to conditions we once thought were sterile. The dramatic reversals in Earth's own deep-time diary tell astrobiologists to look beyond a simple band of orbital real estate. They must search for planets with active, breathing geology and complex atmospheric chemistry, worlds that are not merely positioned in the right place, but are dynamically managing their own climate, just as ours has done for billions of years. The grand planetary rhythms that dictated the age of dinosaurs did not cease with their passing. They continued their slow, powerful beat, and in doing so, they carved the path for our own ancestors. The story of humanity is in many ways a climate story. Deep in Africa, a profound shift was underway millions of years ago. The continent was growing cooler and drier, a long-term trend that slowly but surely transformed its landscape. Lush, continuous forests began to fragment and recede, replaced by vast, open grasslands known as savannas. For the apes living in those dwindling trees, this was an existential crisis. Their world was literally shrinking beneath their feet. This environmental pressure became an evolutionary crucible. To survive in this new world of open spaces, where trees were islands in a sea of grass, a new way of moving offered a critical advantage. Walking upright on two legs, bipedalism, freed the hands to carry food or tools and allowed our ancestors to see over the tall grasses to spot both predators and prey. It was a revolutionary adaptation born from a changing world. This new posture may have also paved the way for another monumental leap: the expansion of the human brain. A more varied diet on the savanna, including meat from scavenging or hunting, provided the dense calories needed to fuel a larger, more energy-hungry brain. The climate had set the stage and our ancestors stepped into the spotlight, but the climate's influence did not stop there. The ice ages that gripped the planet were not a single, unbroken freeze. They were a dramatic roller coaster of advance and retreat, with shorter, intense fluctuations between glacial cold and interglacial warmth. These rapid shifts in temperature and rainfall created a pump-like effect in Africa. During dry, harsh glacial periods, populations of early Homo sapiens would have been isolated in small, scattered refuges where water and food were still available. Then, during wetter, warmer intervals, these groups would expand, coming into contact with each other, exchanging genes and ideas. This cycle of isolation and connection may have accelerated our cultural and genetic evolution, fostering the ingenuity and social complexity that would become our hallmark. Eventually, a window of opportunity opened. A shift in climate around 60,000 years ago may have turned the Sahara into a greener, more passable corridor, while lower sea levels exposed land bridges. This allowed small bands of our ancestors to venture out of Africa, embarking on a migration that would eventually populate the entire globe. We were not the only humans to walk the earth. Our cousins, the Neanderthals, were superbly adapted to the harsh climates of Ice Age Europe, but when the climate became particularly unstable, swinging wildly between extremes, their small, isolated populations and specialized hunting strategies may have become a liability. The more flexible, adaptable Homo sapiens, with our broader diets and far-flung social networks, could weather these storms. The fate of the Neanderthals stands as a somber reminder that in a world of climate upheaval, resilience and adaptability are the ultimate currencies of survival. From the first steps on the savanna to the epic journeys across continents, the pulse of the planet is written into our very bones. That quest to understand our own origins rests on a single, powerful foundation: the ability to read the planet's own diary. Every insight we have explored, from tropical poles to mass extinctions, comes from a remarkable fusion of human ingenuity and cutting-edge technology. This is the world of paleoclimatology, where scientists act as detectives, using sophisticated tools to interrogate the silent witnesses of stone and ice. The most crucial evidence often comes from the deepest places on Earth. Specialized research vessels like floating cities brave the open ocean to drill into the seafloor. They lower long, hollow pipes that can bring up continuous cores of sediment, cylindrical timelines that stretch back tens of millions of years. Each layer of mud and microscopic shells is a page in the planet's climate history, undisturbed and waiting to be read. In the frozen polar deserts, other teams drill vertically into the ancient ice sheets. These ice cores are another form of time capsule. Trapped within the tiny air bubbles in the ice are pristine samples of the ancient atmosphere, a direct measurement of past levels of carbon dioxide and methane. The deeper they drill, the further back in time they travel, recovering ice that fell as snow over 800,000 years ago. But retrieving these cores is only the first step. The real magic happens back in the laboratory. Here, scientists use instruments of incredible precision, like mass spectrometers, to perform a kind of chemical detective work. They vaporize tiny samples of those ancient fossil shells or melt those trapped air bubbles. The machine then sorts the different atoms by weight, allowing researchers to measure the exact ratios of different oxygen or carbon isotopes. This is how they translate a piece of rock or ice into a precise temperature or a carbon dioxide level, reading the chemical language of the past with stunning accuracy. This global investigation does not stop at the ground. From high above, a fleet of satellites keeps a constant watch on the modern Earth, measuring the retreat of ice sheets, the health of forests, and the temperature of the ocean surface. This real-time data is vital for understanding how our planet is changing right now, and it provides the essential baseline for testing our models of the past. All of this information, from the deep sea cores to the satellite feeds, flows into supercomputers. Scientists build incredibly complex digital simulations of the planet, virtual Earths where they can input ancient geography and atmospheric data to see if their models produce the warm, wet poles we see in the fossil record. When the simulation matches the evidence, it gives us confidence that we are understanding the fundamental physics that have always governed our world. This entire endeavor is a testament to international collaboration, with researchers from dozens of countries sharing data and insights, slowly and meticulously assembling a fragmented story into a single, coherent narrative. It is a human achievement as profound as the history it uncovers, turning silent stone and ancient ice into a story that speaks directly to our future. Our ability to read the planet's deep history comes with a profound and unsettling responsibility. We have decoded the warnings etched in stone and ice, and in doing so, we have crossed a philosophical threshold. The story of Earth's climate is no longer just a tale of ancient volcanoes and shifting continents. It is now undeniably a story about us. We are the first species to become a conscious, dominant geological force, capable of altering the planet's fundamental systems on a global scale. This knowledge transforms our relationship with the world from one of passive inhabitants to one of active stewards. We hold the thermostat for future generations in our hands. What is our ethical duty to those who will inherit the world we are shaping today? The deep time record shows us that the climate changes we set in motion will echo for millennia, long after our cities are dust. This raises a question of intergenerational justice that has no precedent. Do we have the right to unleash a cascade of changes that will inevitably limit the options, the safety, and the prosperity of our descendants? The fossil record is a graveyard of species that could not adapt to rapid climate shifts. We now possess the unique foresight to see the dominoes beginning to fall, and with that foresight comes a moral imperative to act. The data is our compass, and the past is our map, pointing clearly toward the necessity of preserving a stable and habitable world. Our choices today are being written into the geological layer that will define our time, a permanent testament to how a species with the power of foresight chose to use its brief moment in the sun. Despite the volumes of Earth's history we have learned to read, entire chapters remain frustratingly blank. We have charted the broad outlines of ancient hothouses and ice ages, but the precise mechanisms behind the most rapid climate lurches are still shrouded in mystery. What was the exact sequence of events that pushed the planet over the edge during the Great Dying? Did the Siberian traps alone release enough carbon, or was a massive methane release the final, fatal blow? And after such devastation, how did life not just return, but explode into new and wondrous forms with such breathtaking speed? The fossil record shows us the recovery, but the biological ingenuity that powered it, the first pioneering species that reclaimed a poisoned world, is a story we are only beginning to piece together. There are even deeper rhythms at play, cycles that operate on scales of tens of millions of years, driven by the slow, grand undulations of tectonic plates that we can only infer from fragmented evidence. To find these answers, scientists are launching ambitious new voyages of discovery. International ocean drilling programs are sending ships to the most remote seas, extracting longer and deeper sediment cores than ever before. Each new core is a fresh scroll, potentially holding the chemical signature of an unknown climate event or a previously undiscovered extinction. On land, researchers are developing more sensitive proxies, searching for new chemical fingerprints in ancient soils and rocks that can tell us not just about temperature, but about ancient rainfall, wind patterns, and even the acidity of long-vanished seas. This relentless pursuit of the past is not an academic exercise. It is a vital race to understand the full repertoire of our planet's climate system. Every unanswered question we solve adds another piece to the puzzle, revealing the true sensitivity of Earth's thermostat and the resilience of its biosphere. The future of our own civilization may well depend on the secrets we can still uncover from deep time. Our planet's long journey has taken it from the steamy, dinosaur-inhabited world of the Cretaceous to the icy, glacial world of the Pleistocene. This epic transformation was not a random sequence of events, but a symphony conducted by three powerful forces. The slow, grand movements of plate tectonics set the stage, rearranging continents and opening or closing oceanic gateways that rerouted the planet's heat distribution. The level of greenhouse gases in the atmosphere, primarily carbon dioxide and methane, acted as the master thermostat, thickening or thinning the planetary blanket to lock in warmth or release it. And finally, the gentle, predictable wobbles in Earth's orbit, the Milankovitch cycles, provided the underlying rhythm, the metronome that timed the advance and retreat of the great ice sheets. This trio of drivers reveals a fundamental truth. Earth's climate is not a static backdrop for life, but a dynamic, ever-changing system in its own right. It is a complex machine with powerful levers, a system that has experienced profound reversals throughout its 4.6 billion-year history. The transition from a greenhouse to an icehouse world and back again is the defining story of our planet's past. Recognizing this deep time pattern is the essential first step to understanding the unprecedented experiment we are conducting today. Our planet's story is a grand epic of transformation, a 4.6 billion-year journey from tropical poles to frozen wastelands and back again. We have traveled through deep time to witness the immense forces that have repeatedly rewritten the world's climate, the slow dance of continents, the pulse of volcanoes, and the gentle sway of our orbit in space. The single most important lesson from this entire saga is one of dynamism. Change is the only constant in Earth's long history, yet there is a fundamental difference between the changes of the past and the one unfolding today. Those ancient reversals were driven by geological processes operating over millennia, giving life time to adapt, to migrate, to evolve. Our current experiment compresses that geological power into a single human lifetime, presenting a challenge of unprecedented speed and scale. The naturalist John Muir once wrote that when we try to pick out anything by itself, we find it hitched to everything else in the universe. This profound interconnectedness is the heart of our planet's story. The chemistry of the air is hitched to the weathering of rocks, the circulation of the ocean is hitched to the fate of ice sheets, and the destiny of life is hitched to the stability of the climate. We are not separate from this system, we are a powerful part of it. We have now learned to read the book of our past, and in doing so, we have been given a profound responsibility to help write the next chapter. What are your thoughts on these ancient alien worlds? Share your reflections in the comments below, and if you have found this journey through deep time compelling, subscribe to continue exploring the great mysteries of our world with us.